We're now going to take a look at what can be considered probably the most important application of these vector functions as far as we're concerned. And what these functions allow us to do is to analyze non-linear motion, right? So going back to your first foray into calculus, you may remember studying things like position and velocity, acceleration, and so forth. But in that setting, you were studying linear motion. So you had an object that was moving either horizontally or vertically. But now with these vector functions, we can suddenly analyze non-linear motion. Right. So let's start with a picture just to give you an idea of why these vector functions will work. So remember, you have an origin, right? And this origin could be in 2 space or 3 space. And from this origin, we define these position vectors. And these are those r of t vectors. So, let's say this is r of t0. And then for different values of t, we get the different position vectors. Let's say it's like this, right? And then let's say then there is like a r of t1, right? And then what we do is we define the terminal point of these position vectors. We use these terminal points to define a curve, right? And now what we're saying is, suppose we have an object on that curve, again, moving along a certain trajectory, right? Right. So essentially, our r of t, these vector functions, and we know how to differentiate them, we know how to integrate them, we know how to find their length, so we can do all those things. This function now defines the position, right, of some particle. So some particle at time t. Right. And this, this position function, it has different names. Sometimes it's called just a path, right? Sometimes it's called a trajectory. So just imagine an object moving along a certain trajectory, and then whatever that essentially that line that it traces out, that's our r of t, right? So if we think back to motion, and I even mentioned some of the quantities that we computed back when we first started calculus, if you're given the position function, well, what are some of the things we can compute? Well, the velocity function, right? So, and again, I'm just going to go through and define a whole bunch of things. I mean, we've dealt with these quantities now. The new thing, though, is essentially everything is vectorized, right? So everything now is in the context of vectors. So the velocity of the particle, remember the instantaneous velocity is the instantaneous rate of change of position. So the rate of change of position would be r prime of t. And again, this is a function that we know how to compute. We're just saying now, if we envision this function being a trajectory or a path, then its derivative will represent the velocity of the particle. And we will use the same v notation for velocity, but now again, it will be in vector form. And then think about the instantaneous rate of change of velocity. Well, that's how we define acceleration. So acceleration, several ways you can say it. You could say that it is the first derivative of velocity, or you can say that it is the second derivative of the position function, and we still use a of t to represent it, right? But again, this is a vector function, hence its first and second derivatives are both vector functions, right? Now, the other thing that I want to define in this initial group of quantities is the speed, right? So the speed, well, the speed is the magnitude of velocity. See, the velocity vector will have both a magnitude and a direction. Well, its magnitude is what we define as the speed. So I'll write it down so that we'll just say that the speed is the magnitude of velocity. Well, velocity is, it's this, right? And I'll write it both ways. I'll write it with the V notation and the R prime notation. And the reason why I'm writing this down, I want you to think back to when we determined how to find the length of one of these vector curves. We came up with an expression that involves a certain magnitude, right? And it's not surprising that we see it back here, right? Okay, so you have velocity, acceleration, and speed. Now let's just make sure that we make it very clear that our position is a vector, right? Because it's going to have some magnitude. The magnitude of r of t, that represents how far the object is from the origin. And then, of course, the direction, it determines in what direction the position vector is pointing, right? So our position is a vector. So is the velocity. So is the acceleration. However, our speed is no longer a vector, right? So speed is not a vector. So this is a scalar, right? So our position, velocity, and acceleration will all have components. Speed will not have a component, right? It will simply be a scalar. All right. So again, these are three important quantities that we have to know how to compute. There are two more that I want to mention, and it has to do with distance versus displacement. So let's say now our particle moves along the curve. And again, it's not traced out perfectly, but we have a particle that moves right there. And then, so our particle starts at this position. Again, it's either in the plane or in space. It moves along that trajectory, and then it ends up there. And this motion occurs over the time interval t0 to t1, right? So basically, let me just write that down, that our time interval is this t0 is less than or equal to t, less than or equal to t1. So two important questions. First, and this is the easier of the two, what is the displacement of the particle, right? Well, let's see if we can define displacement in words. So displacement and then I'll write it in words, and then we'll give you the symbol. So displacement is the change in position, right? That's the formal definition of displacement. So as the object moved, or let's use the past tense, as the object moved along this curve for during the interval t0 to t1, What was its change in position? Well, let's see. This is the particle's initial position, and this is its final position. So the change would be the difference between these two positions. So I can actually draw another vector that would indicate its displacement. So the displacement of the particle, right, would be this vector, right? In other words, you know, this is where it started, this is where it ended, right? What's the change, right? So, and that's displacement. So since it's a change, we're going to use our delta notation, right? Uppercase delta. Well, what is changing? The position, right? So it's the change in our position vector. And then what you can do with this notation to indicate that the time interval that's being considered, we can put the interval at the bottom there. So this is the change in the position of the particle over the interval t0 to t1, right? Well, if I have my position function, yeah, it's where the particle ended. So it's, you know, the position at t1 minus where it started, the position at t0. And again, your displacement is now a vector, right? The displacement is now a vector, so that's also a vector. In fact, let me write it down here. The reason I'm writing it down here is because there's an alternative formula for displacement, right? Now, when you think about this change, think back to Cal 2. This change is I'm not going to say it's a net change, but a change can always be represented by an integral, right? So let's think about it. Our fundamental theorem says, you know, you find an antiderivative, you plug in the upper, you plug in the lower, and you take a difference, right? So based on the limits, I should be able to represent this change as a definite integral, right? Because those are my limits. T1 is the upper limit, T0 is my lower limit. But now if you think about the fundamental theorem in reverse, it's basically saying that my R is the antiderivative of some function. Well, if you think about it, what would the antiderivative be of, or what would the position function, right, be the antiderivative of, right? In other words, what would I have to integrate to get position? Well, think about it. If I differentiate position, I will get velocity. Therefore, if I anti-differentiate velocity, I will get the position vector. So here is an alternative formula. So these are two formulas that can be used to compute displacement. If you know the position vector, right, and you have your time interval, then just evaluating and taking the difference will give you the displacement. If you know your velocity vector, then we would have to integrate over the time interval t0 to t1, right? And again, this is all based on two things: the relationship between position and velocity, and our fundamental theorem, right? So this assumes that our velocity function is integrable, and all the velocity functions that we're going to be working with will fall into that category, right? So that's displacement. The last quantity that I want to mention now is distance traveled. Right, so we're going to look at the distance traveled. Well, let's go back up and look at our trajectory. So the distance traveled now is what I have highlighted there in green. That's the actual path that the particle took to get from this position to this position, right? Should have got some nice theme music there, right? But yeah, that's the thing. So if we could figure out this distance traveled, right? This green, that goes from here to here, then we would figure out the distance traveled. Well, what is this thing? Well, essentially, that would be the length of the curve, right? That would be the length of the curve. So if I could figure out the arc length of my position function from this point to this point, that will give me the distance traveled. So whereas, just to find displacement, it's just another position vector. Well, technically it's not a position vector since in general it doesn't have to start at the origin, but it's just a regular vector that represents a change, whereas we're going to use an arc length to represent the distance traveled. Essentially, how long is that green curve that I drew, right? So distance traveled, this is going to be our formula. Well, let's see if we can remember our arc length formula. It's an integral, and we know it's going to go from t0 to t1. And it was, so there are two ways we could represent it. Let's see if we can remember our square root expression. So it's the derivative of the component, right? So for instance, let me write down r of t. So let's say, so in this case, I will have to, if I'm using this notation, I will have to pick whether it's R2 or R3. I'm going to go for R3 so you can see the full formula. But remember, if your vector function is in this form, its arc length is given by the derivative of x squared plus the derivative of y squared plus the derivative of z squared. Take the square root and integrate that. But this is precisely the magnitude of the derivative of this function. So let me write it like this. Yeah. So that's why I wrote this other notation here, right? Because that's kind of the compact shorthand notation for this expression, right? So you're finding the magnitude of the derivative of the position function, and then you integrate that from t0 to t1. But we just stated up here that the magnitude of the derivative of the position function, that's simply the magnitude of your velocity. So what this is saying, to find the distance traveled, what you have to do is integrate your speed, right? And that makes sense. That is actually consistent with all the formulas that you'd have learned in physics, for instance. The difference now is we're allowing the path or the trajectory that our object is on, we're allowing it to be non-linear. So in many cases, if our speed doesn't come out to be a nice constant, then the integral might be a little tricky, right? But we have all the calculus techniques that we need, right? So there we go. We've essentially just taken our concept of motion, made it non-linear, and vectorized everything, and we've come up with these really useful formulas. Now there's a lot more that can go in to this, but I just wanted to start with these 5 basic quantities. And you're typically going to be given the position function, although sometimes you might be given velocity and asked to work backwards and find the position. But before we jump into our example, I want to finish this kind of list here and notice that distance traveled is also going to be a scalar. All right. So for speed and distance traveled, you're going to get a number right, as the final answer, whereas for velocity, acceleration, and displacement, you are going to get a vector. All right, so let's do an example. I will use one curve, right, one trajectory to illustrate all of these. So let's do this. So let r of t be equal to, and let's do this. Let's say it's 8 times the square root of t cubed, and then we have the sine of 2t, and then the cosine of 2t. So let this be the trajectory of an object traveling in R3 for, and let's use the interval, let's say 0 to 2, right? So like this. All right. So let's go through and compute a few things. So let's go ahead and find, so for part A, let's find the velocity function and the acceleration function, both of which will be vectors. So v of t is the first derivative of position. Now, the only thing that you have to be careful of when you're, for this particular one is like, how are you going to handle the square root of t cubed? It's probably easiest to write this as t raised to a single power. And if you use your properties of exponents, you'll get that the square root of t cubed is t to the 3/2, right? So with that in mind, let's go ahead and use our power rule. So bring down the 3/2, multiply the 8 times 3/2 is 4, and then you'll have t to the 1/2 after you subtract 1. Remember, we're differentiating now. And then we need our chain rule for both the second and third component. So sine of 2t is 2 cosine of 2t when it's differentiated, and then the derivative of the cosine of 2t is negative 2 sine of 2t, right? So there's our velocity vector, and then differentiate a second time. So I'll just say that our acceleration is the derivative of velocity. And again, we can use our power rule another time. So bring down the 1/2. So we'll have 4 times 1/2. So that's 2t to the negative 1/2. And then here we will have a negative 4 sine of 2t. And then here a negative 4 cosine of 2t, right? And that's our velocity, our acceleration vector, right? And okay, good. So let's find, so part B, let's find the displacement of the object, right? During this interval. So we'll just use the interval 0 to 2. So find the displacement of the object. So our displacement over the interval 0 to 2, I'm just going to use my use the algebraic way of computing the displacement. In other words, evaluate the final position, which is r of 2, evaluate the initial position, which would be r of 0, and then take the difference, right? So if I plug 2 into the original function, so what would that be? I have, okay, so if I plug 2 in, I'll have 2 cubed, which is 8. In fact, yeah, let me write it like this. So we'll have, it's too big of a root. So we'll have 8 root 8, and then the sine of 2 times 2, that's just the sine of 4. And then similar, the cosine of 2 times 2, so that's the cosine of 4. Right, so this is r of 2, and then let's subtract from that r of 0. Well, when I plug 0 in, the first component will be 0, the second component will be 0, but the third component will be 1, right? So what this means is, remember, this is the initial position, right? So this means that the object started its motion at the point 0, 0, 1. So basically 1 unit in the positive direction on the z-axis. That's where the object started moving from, and then this is the point at which the motion ended, right? So when we take the difference, we'll have 8 root 8, and then the sine of 4, and then the cosine of 4 minus 1, right? So now, all of these numbers are irrational numbers. I'm just going to leave it in this form. No need to really approximate it, right? But that's the displacement of this object, right? Part C, let's find the speed, right? So find, now the speed, I'll use this notation for it, right? The magnitude of the velocity function. Well, here is the velocity function, so we have to compute its magnitude. So let's see how that works. So we're going to square the component, so let me write it down. It's going to be 4t to the 1/2 squared plus 2 cosine of 2t squared plus negative 2 sine of 2t squared, and then we're going to take the square root of that. Right, so notice right away as we look at it, this is the first thing that we've computed now. It doesn't have any components, right? It's a scalar expression in terms of t. Well, let's simplify this scalar expression in terms of t, see what we come up with. So the quantity 4t to the 1/2 squared, that is 16t, right? And then let's see. All right, I actually think let me go back and look at something, because I think I have an error here. Yes, so this needs to be corrected. This should be 12, not 4, because I didn't multiply by the 3, because remember we brought down the 3/2, so this should actually be 12, and that would affect this. So then this is 6. There we go. So that's 6. Now, thankfully, we haven't used, so we didn't use either of those vectors in part B. So this one is still, so B is good. So then this 4, that's in front of the t to the 1/2, that needs to be a 12. Yeah, so that's 12, which then changes this. Okay, good. I'm glad I caught that before we went too much further. So we have 144, and then t, and then plus. So squaring this gives me 4 cosine squared of 2t, plus squaring this gives me a 4 sine squared of 2t. And again, that's all under the square root. Now, always look out for patterns where you have cosine squared of something plus sine squared of the same thing. So the fact that the two inner functions here are the same, 2t, it means I should be able to simplify this quite a bit. So I'll have the 144t. If I factor out of 4, out of the middle and the third term, then I'll have the cosine squared of 2t plus the sine squared of 2t, but that's equal to 1. So this is equal to 1. So here's my speed function. It's the square root of 144t plus 4. And we can actually simplify this. I can, under the square root, I can factor out of 4. And then that gives me, what do we have there? 36t plus 1, but that's all under the square root. And then now, since I have the square root of a product, I can take the square root of 4 times the square root of 36t plus 1. So here's a simplified version of my speed formula. It's 2 times root 36 plus t, right? Okay, so that's our speed. And then let's do part D and say, what is the distance traveled by the object, right? And that's where we now use our integral. So the distance, now what formula are we going to use for distance? We're going to use the letter S. S is often used for distance and arc length. That looks more like a 5. So the letter S, this will be used to represent distance. And it's the integral now from 0 to 2, and I have to integrate my speed. So I have to integrate this function. So I'll have 2 root 36t plus 1 dt. So what are we going to, what integration technique can we use here? Well, I think a standard u sub will work. So I'm going to let u be the inner function here. The 36t plus 18, that means du is 36 dt, right? And now I have a 2 already here, so if I take 1/18 of both sides, so if I multiply both sides by 1 over 18, then I'll have the 2 dt. So I can get rid of that constant, right? There are other ways you could do it. I'm just choosing to substitute for the 2 dt and then everything that's under the square root. And I always change my limits of integration. So when t is equal to 0, u is equal to, that would just be 1, right? When t is equal to 2, so double the 36, so that's 72 plus 1, so u is 73. So now I've completely transformed this definite integral to an integral with respect to u instead of t. So my limits are 1 to 73. The 2 dt becomes 1/18. So say 1/18 the u, and then I have the square root of u right there, right? So let's factor out the 1 over 18. We have 1 to 73, and this is u to the 1/2 du, and then use our power rule now for antiderivatives. So we have 1/18, and then so adding 1 gives me 3/2. Dividing by 3/2 is the same as multiplying by 2/3, and then I'll have u to the 3/2, and then my limits are 1 and 73. So 1 over 18 times 2 over 3, that is 1 over 27. So I'll put that there. And then at the upper limit, we'll have 73 to the 3/2 minus 1 to the 3 halves. And yeah, so I'll just, so again, if you want to, you can go ahead and get the decimal approximation. I'm going to leave it in the exact form. However, I'm just going to remind you, again, properties of exponents. I can write 73 to the 3 halves as 73 root 73. And then obviously 1 to the 3 halves is 1. And whatever units this is, that would be the units of distance, whether it's miles or millimeters or any measure of length. All right, so there we go. Just being able to now compute familiar quantities, right, but for slightly different functions. And the big advantage that we have now with these vector functions is that our motion does not have to be linear, right? It can cover it in the linear form, right? Because remember, we have a way of defining lines, right? We have a linear form of these vector functions, but we now also have these non-linear forms. So hopefully you found that interesting, and I'll see you in the next video.